The next presentation series is going to focus on how environmental science can impact Mars exploration. So let's get right into it.
Hi, I'm Nikhil and I'm in ninth grade.
I'm Katie and I'm in 10th grade.
I'm Pranav and I'm a sophomore.
I'm Mario and I'm a 10th grader.
And our project aims to create an efficient method to mine ice on Mars.
On Mars, water can be very hard to find due to the planet's atmosphere. When water is brought above the soil, it evaporates, and this is due to the atmosphere's supersaturation. If we were to colonize on Mars, we would need an efficient way to bring water back to their base and filter it before consumption.
So there are two main options for water extraction on Mars. The first method involves directly digging or drilling ice. Mars's northern ice cap is 621 miles long, and in many places, ice can be found less than a foot below the surface. So the ice can usually be dug out with a shovel or drill. The other option is extracting water from Martian soil. Each cubic foot carries about 2 pints of water.
Every human needs about 2.7 to 3.7 liters of water a day on average, not including the watering of plants for food. Soil may be more abundant, but if astronauts decide to use soil, they will have to dig about 240 cubic feet every month per person. To power either of these operations, solar power is a capable method. NASA's 2 Mars exploration rovers were able to produce 410 to 900 watt-hours of energy per Martian day, which is 2.7% longer than an Earth day on Mars. The average microwave oven uses 1,200 watts and need to power a device, so our solar power system will need to be larger.
Considering data from NASA's Mars orbiters and rovers, our rover will have to land between 40 and 60 degrees north latitude and 130 and 190 degrees east longitude, where there's plentiful sunlight but a cold enough temperature for ice to exist. Landing in the northern hemisphere is also beneficial because it is generally lower in elevation and provides more atmosphere to slow down a landing aircraft.
600-watt solar panels first became available in early 2020. 3 of these panels should be enough to power operation. However, as the seasons change, power generation can be reduced by an estimated 65% due to dust and changes in the distance and position of the sun. This can be partially reduced by regularly cleaning the solar panels, but we might need up to 6 more solar panels as a backup. Although the production of solar panels results in greenhouse gas emissions, they will be made up for as the panels are used.
Our system will be a rover that goes to the northern ice cap, retrieves water, and cleans it before bringing it back to the astronauts. It will house a camera, airtight container, drill, and specialized wheels for traction and durability.
Our robot can use a thermal sensor to locate ice because ice changes the temperature of the surrounding surface. Alternatively, a moisture sensor can be used to detect spots where ice has been building up. The robot will use a built-in drill to dig the soil. The drill will be programmed to distinguish solid ice from soil. After this, a box will drop to the ice's surface and begin cutting a square the shape of the container out with built-in knives on the robot. The box will have a suction-like material that will be used to have the ice stick to the box while it is being collected. The ice will be retrieved and brought back to the astronauts.
At the base, the ice will be loaded into a microwave of sorts contained in a life support unit that's already being researched by the Mars 1 mission in the Netherlands. This microwave will heat up the ice and turn it into water vapor, which will then travel up a seal tube into 2 safety filters. These filters will further clean and distill the water, polishing it to NASA's standards of clean water. After going through the filters, it's fed into a containment unit that is able to hold up to 1,500 liters of water. Thank you.
Okay, thank you so much for your presentation, guys. I'm sorry about the slides.